right, so we're going to look at what's due today first. So I want you to look at number 4. And when you used the interval from 0 to 4 pi, what did you notice? It goes around twice, right? Because remember, these graphs, it's not just about getting a graph on there. It is about what is happening to whatever. A lot of times what's used generically for parametrics is some particle that's moving, because it could kind of be anything. There are tons of applications to parametric equations with conic sections and some other things right now. Even though I know you've done them to some extent in physics, we're still just kind of in the introduction phase, purely mathematically. So it goes around twice, because remember, when you graph it, and it is a circle, so I'm not even going to put it on a coordinate plane, but it is a circle that you end up graphing, and then remember that you're supposed to have like the motion, and so what's happening is it's going around. And if you want to know how far this particle moved from its starting position, and it starts and it goes around the circle twice, then the distance that it traveled is going to be twice the circumference. Does that make sense? So that is the purpose behind that interval, is we want to know how much did it actually go, because maybe it only went from 0 to pi, and then you just get a semicircle. You don't even get a full circle. So you know how much and the actual path of what's happening. Okay, does that make sense there, if you were wondering about that? Did you have any other questions on this? Anybody have any questions on any of it? We're all good? I did not have a chance to ask anybody, because there's really only, the question was, did I have a chance to figure out what to do about the range on number 3? I did try and look for the answer myself, because I don't know the answer to that question, and because you can't just start at, what would it be? Or you can't just end at 2, because it's really going to go farther than that, but it can't go, all the way to t equals 0, because it's undefined there. But how you actually define that as a range, I don't have a good answer for that yet, but I'm working on it. And I couldn't find the answer myself, and I tried. Number 3, when it asks you for the range, that was the question yesterday, like, since it goes from 0.4, right, up to the last thing you can plot is 2, but when time starts at 0, time doesn't actually happen in whole seconds, right? There's a half a second, at half a second, if that's time or whatever it may be. Maybe it isn't defined there, because maybe t isn't, maybe it isn't a fluid thing, but then we wouldn't connect the dots. So since we're connecting the dots and making it a smooth curve, we're assuming that it does continue. So, but either way, whether it's time, temperature, whatever, it could be half a degree or half of a second, and it is defined there. So it's going to go all the way up to where t equals 0 but not touch it. But since we don't know what that y value actually is, we can't have a top tier for the range. And I don't know how you handle that. What I have on here, which is just the key that somebody else worked out, says that y is greater than or equal to 0.4, but that's not true, because that includes, up to infinity, and clearly that's not right. And so I didn't even catch that when I was looking through these, because I was working them, but just kind of working them and making sure that all this stuff made sense, but I missed that. But that is a very good question, and that's going to continue to bother me, and I will get the answer. I just haven't had a chance. Anything else? All right, so then go ahead and stack them up. It's okay if they're not stapled. Just make sure at least your first name's on the graph paper, and they'll stay stacked together. There's so few of you, it's all fine. So now what I want you to look at is this, the yellow paper that I just gave you. And really, we're going to look below the ellipse part. So look at the side that has the ellipse, and then there's 3 graphs underneath it. And it's these 3 graphs that we are going to look at real quick, just to talk about what's happening here. Now, if you just look at the parabola itself on all 3 of these, is it the same? You get the same piece of the parabola, right? And what you see is the graphs look exactly the same. So it says, use each parameter to write the parametric equations that can represent y equals x squared minus 4. That's why it looks the same, because it's all representing that, right? So our parameters change. At first, we use t equals x. The next time, we use t equals 4x plus 1. And then the third time, we use t equals 1 minus x over 4. So here's what I want you to see here. When you change the parameter, the equation itself doesn't change. But here's what does change and why the direction is important, and also for you to understand like the speed at which something is happening. We can see that whatever's happening, we'll just use the particle moving. I would start here and I go like this on all three of them, right? But what changes is how quickly that happens. Here is -2 to here. This is basically goes from -3 to 3. This goes from -11 to 13, so it would take longer, basically, if you're thinking of time, and I know it's negative, but, and then here, 7/4 to 1/4, and so that's like a whole lot faster than these two are. So what's changing when you change your perimeter is maybe the speed at which something's happening, and it's not always time and speed, but those are kind of the easiest things to wrap your mind around right now. So moving in the same direction, but changing the parameter changes how fast it's going, but you still have the same XY relationship. Okay, does that make sense? And you don't have to, you know, making you come up with these parameters. I just wanted you to see that sometimes you might graph the exact same graph, but when it asks you to recognize what's happening, it is, oh, I was told, and this one goes this direction, sorry. This one goes this direction, but see how the direction even changes on that one? It goes faster and it goes in a different direction because the parameter changed. So direction and time can change with those. And that's kind of what I wanted you to get out of this today. We'll look at this again tomorrow, but I just want to go ahead and give it to you to talk about this, okay? If I want to know distance, if this was actually a particle moving and it starts here and it moves like this, all three of these move the same distance, different directions, but it's the same distance. So it would be the length of whatever this parabola is. And we haven't figured out how to find the length of that kind of curve yet. That's okay. We're going to estimate it a little bit differently. And then that's kind of what you end up doing in calculus. You take that estimation and you make it more and more and more and more accurate with the calculus that you actually do. And we're not going to look at the calculus. We're just going to do the estimations, and we'll talk about how you make it better and better. Okay. Any questions about just looking at those graphs right now? All right. So what we're going to do today is we're going to do an LTF activity because I found this. I know I probably shouldn't even use those words, but here's the thing about LTF activities. I think they're all fantastic. Some of them are like way out there, and they give you questions that like make your brain hurt. You can't even focus on. And that's not a bad thing because you need that sometimes. This one's really not that bad. There's nothing outrageous about anything on here. Okay, so I'm just going to tell you that up front. If it was, I'd be honest with you and tell you, you're going to have trouble with this one, but I want you to think through it and, you know, try. But this does a good job of kind of showing what's happening with parametrics and why we need it and things like that. I don't think that that's always very obvious to you. And we're also going to graph them on the calculator. So I need you to clear the RAM on your calculators so that all the settings are back to the beginning so we don't have any issues. I'm going to do that on mine too, and then I have to change my... Okay. There's the third one. Did you give him what he needed? Cody? You turned it in, whatever it was. Okay. Yeah. All right. So here's mine. So these are all going to be a generic kind of a particle is moving type of thing. Here we go. So a particle moves so that the position is measured in feet. Okay, so this is important to us. At any time t seconds from 0 to 4, and it's given by this set of parametric equations right here. Right? And so we're going to complete the table below, which should be fairly simple, right? So if t is 0, x is what? -1. -1. If t is 0, y is what? You want to do all the x's first? Is that better? Is that why you're stumbling? Okay, let's do all the x's. Okay, so I'm going to plug in 1 to the x. So I plug in 1, and then what do I get? 1. I substitute in 2, and I get 3. Substitute in 3, and I get 5. I substitute in 4 and get 7. Okay, you good with all that? Right. So I substitute in 0 to y, and I get -1. I substitute in 1, and I get 0. Substitute in 2, and I get 2 squared 3, okay. Substitute in 3. I know these are really hard questions. 3 squared is 9 minus 1 is 8. But that's how you mess up on the easy stuff, right? Like it happens. 4 squared is 16 minus 1 is 15. Okay. So there's graphs there, but let's read what the directions say. The directions say graph the path of the particle on the calculator, then transfer the graph to the paper, making sure the scale is correct. All right, so you have kind of done parametrics in physics. Have you graphed them on the calculator? Does that sound familiar? It's okay, I mean, if you don't think you did. So when we go on the calculator, well, I got an x and a y. If I'm on my calculator and I go to y equals, do I get to do that? No, right? So instead, we have to change our mode. So when we go to mode, you know, we've already changed it to polar to graph. The PAR is parametric. So when we go down to parametric and we change our mode, now when you go to y equals, you actually get x and y equals. Okay? Here's a little hint from mistakes that I've made, I think only once in the last week, is make sure you actually put x and x and y and y. Because I flipped mine around and I was like, what the heck, I knew it wasn't right. So yeah. And it's not that hard, but you know, it's one of those stupid things I did. So we're going to type in exactly what we see. So for the x, we get 2 times t. Well, look, t is right here with this. That's why you have x, t, theta in, because depending on what mode you're in, it changes, just like we had theta for polar. It is a capital T. That's one thing that people complain about with the TIs, but it is what it is. It's fine. It means the same thing. Minus 1. Then I go down here, and I've got t squared minus 1. Okay. Then we're going to graph it. All right, now, we have just our generic window. So let's look at what we have. When you are given a graph, and they expect you to graph it on there, and it looks something like this, well, you know what? Chances are pretty good what you're trying to graph isn't mostly in the second quadrant. That's why they gave this to you, right? And so let's think about what a window would be that would make some sense. Well, this goes from -1 to what? 7. And then y goes from -1 to 15. And you can kind of tell from your data too, but sometimes the graph itself has a little bit more just so you can see it. But this right here looks like a decent window because that's all I got to graph on anyway. So now that's when you change your windows, when you know what you want to change it to. Don't worry about Tmin and Tmax. Don't worry about the step. You can change those things for reasons if you need to later or whatever. But we're going to go to the x, and that was going to be a -1. X max was going to be 7. Y minimum is -1. And Y maximum will make 15. So now when you graph that, okay, it gives me the part that I'm supposed to be graphing. But what is the difference between what you have here and what's on your paper right now? It's what? The scale, right? We're actually counting by 1s and counting by 15, but the difference is my 1 on the x scale is bigger than the 1 on the y scale, right? And so I'm not sure if did we actually graph circles on the calculator in here this year? Okay, no, all right. I know we did it in geometry, and I just recently did it in geometry, that's why I couldn't remember. So basically, everything you graph on these calculators, when you just let it do its own zoom and window and stuff, is distorted. Because this screen that you have, even if I wasn't trying to get a graph that isn't square anyway, is rectangular. So everything's distorted. You just can't always tell, and it's not that bad. What I want is for my x and my y to be the same width here, right, the scale-wise, without me having to guess as to what I need to change my x to. So if you go to zoom, 5 is square. Like I fix my window to what I want and what I want to see. Zoom 5 is z square, and it squares up your graph so that if you had a grid behind it, the little squares would be squares and not rectangles, and things aren't squished. Does that make sense to you? So that's going to look way more like what you're actually trying to graph on your paper. Now it says now transfer it. We don't need to go to the table in the calculator and do all that. I mean, we have the table. We honestly could have graphed it without looking at it on the calculator, but I wanted you to do this too because we're going to look at something else here in just a second. So we're going to go over here to this one, and we're going to plot these points. So -1, -1, then 1, 0. It's okay. And then 3, 3, 5, 8, and 7, 15. Oh, my shadow on the board, I can't even see where I'm trying to line up. Okay, so about right there. And there's no arrows because we have actually a closed interval. Then I'm just going to do my best to make the curve. Oh, see, do my best, and that's not very good. Dang it. It's too far away from you. All right, well, I think it was better the first time. You can pretend like that's good. It's easier to do on a smaller piece of paper. All right, so everybody have their curve? Now my particle, how is my particle moving? Does it start at the bottom or at the top? At the bottom, so it's moving in this direction. Now here's something else you can do with parametrics, is that you can actually see how it moves. If you don't have a table, if you're just going to go and graph it, so let's go back to the calculator, and I want you to go back to mode, and you're going to leave it in parametric, but I want you to go down here. You see where it says sequential, and then that says simulate, so arrow over, and change that to simulate, and then graph it, and it graphs it in the direction of the movement. Whereas normally when you, what I don't know how to do, and I know there's a way, is once it graphs it once, how to make it do it again without changing something. And I know there's a way, but I couldn't remember how to do it, and I tried everything. So what you saw is it went like that, right? Instead of coming down like this. Because if I change my parameter, I could have the same graph, but it go in a different direction. So it's kind of telling me that. You just have to pay attention. And then if I ever can figure out how to make it simulate again, because like now if I go back to y equals, it just shows me the graph. And unless I change, oh, that's right, thank you. I go over there and I change that. I knew there was a way, I just couldn't remember what it was. There you go. And then it'll do it every time. Yeah, there you go. Remember how we did that? We did that when we graphed something else. If you go to back to y equals, and it's really changed it on the x, you arrow all the way over to the left, hit enter a couple times till you get that little thing. And then remember, every time you hit clear, it clears that off too. But then when you graph it, it's still just, did it once. But there's a way to force it to do it every time, and I don't remember what that was. But that's okay. You only really need to see it once. All right, so then, come back over here, and it says, on your graph, plot the points from the table and connect the consecutive points with line segments. So basically, we're going to do that on this one. We are not going to just plot the points and make a curve. We're going to do what you're usually not supposed to do. And we're going to replot the points. So I'm at -1, -1, same points. 0, 1, or 0, 1, 0 rather. And then 3, 3. So this time, instead of trying to make it curvy, use a straight edge though. I did it freehand, and of course they weren't super straight. Use your ID because it'll make a difference in what you see. And then connect the dots. Because here's what we're going to do with this. What I want to know, I know what direction my particle moved in. I know how far it went horizontally and how far it went vertically, because that's what these things give us, right? And I know those things, but what I want to know is how far it actually moved. Well, if it moved in a straight line, okay, if it just moved and it went like this, then if I can figure out the horizontal distance and the vertical distance, I could use Pythagorean theorem and figure that out, right? But this isn't a line segment, this is a curve. So we don't know how to truly treat those curves just yet. So what we're doing instead, and you can do it on this graph too, it's just not as not as noticeable, I guess, because your curve probably isn't perfect. But if you think about connecting those dots on this graph, does it follow the curve pretty closely? Like if I just connected these two dots with a line segment instead, it's close to that curve, right? And the farther up I get and the more vertical I get, the closer and closer it actually is to that curve, right? So the best we can do right now to estimate the distance is to find those distances and add them up. What we're actually doing here is finding average rate of change. Okay, what's another word for rate of change? Slope, okay? So slope is rate of change. We know how to find slope. If I had this line segment, we could find the slope of it, no big deal, right? You don't know how to find the slope of a curve. So there is average rate of change, and then there's instantaneous rate of change, okay? And you use those when your rate of change changes. Okay, now we did something, and I know I keep referring back to geometry like I'll remember it like it was yesterday, but we did do an activity where there was a ladder sliding down the wall. And one of the things that you're supposed to figure out from that is that they give you a rate at which it gets pulled away from the wall, but the rate at which the ladder comes down the wall is different. It actually increases. So if you ever had anything sliding down the wall and like you're going to catch it and you feel like it speeds up before you get there, it does. Because if you pull it away from the wall at a constant rate of change, which is actually what's happening here, because if you look at your x is linear. So it has a constant rate of change of what? What's your constant rate of change for x? It's an easy question. It's a line 2. Okay, so the rate of change for x is 2, right? It is x, the x value is changing at a constant rate of change, but the y value is not because it's not linear. So they can be different. Okay, that's just like when you throw something, your linear velocity and your vertical velocity are two different things, your horizontal and vertical. So what we're going to do is we're going to find these line segments, the average rate of change. So basically, if I want the slope of this curve, if I want the instantaneous rate of change, then you find the slope of the tangent line at any given point. So at any given point of x, whatever x might be, I could do like 3.7. If I found the slope of the line that's tangent to that curve, that's my instantaneous rate of change. That's a whole lot harder to do for us right now. What we can do is average rate of change. That means we pick 2 points, right? I pick 2 points, and then I'm going to find the slope of the line that goes through those 2 points, right? So if a line intersects it at 2 points, it's not tangent. What's it called? Starts with an S. Secant. It's a secant line, okay? So we're finding the slope of we're not actually finding slope of this, but that's how you find average rate of change. It's the rate of change between these 2 points. Well, guess what? That's not the exact rate of change of this curve. But if I pulled my 2 points in closer and closer and closer, then I would make them closer and closer and closer to a tangent point, and then I'd get the actual instantaneous rate of change. So we're kind of using that idea here, even though we're not finding slope. What we're going to find is we want length. Instead, I can't find the length of this curve, so I'm using the same idea because I do know how to find the lengths of line segments. So we're going to number these. This is 1, this is 2, 3, and 4, just so we have them numbered. Otherwise, we could label them with points and call them A, B, and whatever, but we don't need to do that. So now that we've drawn those little line segments on there, we're going to calculate the length of the line segments drawn between the consecutive points. So if we start with number 1, that means I'm using distance, right? So distance is equal to the square root of x minus x, right? So if I'm going from these, now I could label all my points on here, but I really already have them here. I'm finding the distance between these 2 ordered pairs to begin with, right? I want that distance, and those are the 2 that I'm using. So that's going to be -1 minus 1 squared plus -1 minus 0 squared. So that's going to give me the square root of -2 squared plus -1 squared, right? Square root of 4 plus 1, so I get the square root of 5. That's the length of the first one. Simple distance formula. Then I'm going to go back up to my graph, so now I'm looking for 2. So that means I want the distance between now these 2 points. All right, so I'm reusing that one. So for line segment 2, I'm going to do distance again. That is the square root of, that would give me 1 minus 3 squared plus 0 minus 3 squared. Square root of negative 2 squared plus negative 3 squared. Square root of 13. You get the idea? So you got 2 more. Find the next 2 while I go check roll, and then we'll walk through the rest of this. And I forgot my watch today, and I'm going to go crazy all day. What do we get for the length of the third one? Square root of 29. Good. And for the fourth one, got. And what do we get for this one? Square root of 53. Okay. So there are those lengths. And that's all it asked me to do was calculate the length of each one. Everybody good with that? All right. So I'm not going to walk you through all of these, but I'm going to get you through most of number 1, and then you should have a good idea of what to do. So now it says the distance traveled by the particle that moves on the path can be approximated by summing. Summing means we're going to do what? Add. Okay, summing distances along the line segments between the consecutive points. So if we want to approximate the distance traveled, that means we know it goes the square root of 5 plus square root of 13 plus square root of 29 plus the square root of 53. So you can just type that in on your calculator. Now, a little bit of a warning for the 84s that you're using. I'm not sure what operating system it has, and so sometimes the square root acts differently. It's not that hard to figure out, but if you've never used it before, you get confused, and then everything's under one big square root. So square root of 5, if it opens the parentheses, you have to close the parentheses. If it doesn't and you get a little box, you have to arrow out of it, or it's going to put everything under the same square root. But be careful with parentheses and the boxes here. Square root of 13, close parentheses, plus the square root of 29, close parentheses, plus square root 53, close parentheses. Okay? You've got to actually type that in and not just take my answer from this. Because we're going to take this, we're going to hit enter, bam. That's my approximation. Now, I'm going to need it. Now, regardless of whether or not I know I need it right now or not, it's just something I had to type in all that mess for and got a decimal. If I have to use it again, I need that, right? So I might as well just go ahead and store it. I'm going to store it in X, or actually it ends up storing it in T, and that's okay. I'm going to store it in T, and so it's there just in case I need it. Right? It doesn't represent T, but you could have stored it anywhere you wanted to. If you wanted D for distance, whatever, just so that it's stored. So what it's asking me for is to approximate the distance. So this is approximately 18.507 what? With my units here. Feet. Now, we know that this isn't the actual distance because we connected the dots to make everything linear because that's what we know how to handle right now. But it says, do you think your approximation is too large or too small? And explain your reasoning. What do you think? Too small? Why do you think it's too small? Okay, good. And it's too small because, now we didn't do them on the same graph, but even you could tell if you wanted to do a couple, even from this one that I did, because it curves and we're connecting the dots, that curve is clearly at least a little bit longer than the line segment. Even up here, where mine looks really bad, but even on these, it's still really curving slightly, so it's too small. Okay, because it's too small because we have straightened out our curve, basically. So, too small. And really what you have to be careful with when you say this is, do you really, really know that it's less? Like, it looks like it is, and you think it is, and if you don't have a mathematical reason to back that up, then you need to be careful how you phrase it. It's too small because it appears that the line segments are shorter than the curves. Because this is kind of a what do you think question. I think it's too small. Tell me why. Because you know what? Maybe you think it's too big, and if you had like this amazing reason that nobody ever thought of, then, oh, well, maybe we could take that one too, or whatever. But it's too small because it appears that the line segments are shorter than the curves, okay? They are, but, you know, got to be careful how you word things. All right, I'm going to do one more part of this with you, and then I'm going to turn you loose on it. So it says the speed of the particle can be calculated as distance divided by time. All right, so look, we're looking for speed, right? The speed of the particle can be calculated as distance divided by time. Now, on here, it tells us that our units are what and what? What did it tell us at the very beginning? Feet and seconds. And you should understand how speed works. There's a difference between the units for speed and acceleration and all things like that. So speed, and it even says distance divided by time. Well, your distance in this case is feet, right? Your time in this case is seconds. So your units are feet per second. Okay? Sometimes people get real tied up in, I don't know, how am I supposed to know what the units are? It's speed. It's like miles per hour. We're just talking feet per second. Because then it says, what is the particle's approximate average speed over the time interval? And be sure to state the units. Well, the units are something you know from the very beginning. And if not, you can substitute them in when you do that. Well, we know the distance, or the approximate distance. It's 18.507, but I'm going to do dot, dot, dot because I'm using that from my calculator. Or you can circle it. Remember we talked about those, how whatever works for you. And that is feet. Divided by the time, what's the time? Four seconds. 4 seconds. And when you substitute it in, if you put the units in there, guess what? These don't cancel each other out, so the units are right there also, feet per second. So in your calculator, now since we haven't done anything else, if I hadn't sorted, it's still looking at me. I can just take that, or I could do t divided by 4. But I'm going to divide that by 4 and hit enter. Maybe I need that again. I don't know. So I'm going to store that. And alpha, I'll use S for speed. If I can find S, I can't really read this. Just in case I need it. Then I can say that the approximate speed on this interval is 4.627 feet per second. And you will not always be reminded to make sure you add the units, but you always need to make sure you add the units. Okay? Any questions about that? All right. So, now this is where I'm going to stop with you, because now it says write an equation for y in terms of x. That's something we've already done. You have the two parametric equations. You can solve for t and substitute it in. Then you should be able to find the domain and range. It's not a weird one like on that homework question. And then 2 walks you through some of the same kinds of things. yeah, I don't think there was anything else I wanted to work with you on that. I think I've kind of talked about everything that would be good to look at on here. And just do your best with the curves, okay? Any questions? All right, make sure you're in parametric mode so that you can, you know, graph and do what you need to do when you graph it. But most of these questions are not nearly as hard as you would think because they're LTL. Are we good? Yes? All right.